So I'm going to present my findings on using a hierarchical models to analyze the SPY stock data. So first, I'm going to describe my data set. So I have this data from 1998 up to 2020, includes the COVID-19 period, and on each trading day I have 13 columns. This is because on each trading day there are 6.5 hours, meaning there are 13 half hours, and on each half-hour interval, I will just compute the price return. So, for example, if the price return of the second half hour is this means that the price goes up for 0.021 in this 30 minutes interval. And it also could go down, right? So if it's negative 0.23, this means that the price goes down this amount in this 30 minutes interval. And so for this project, I just have 3 questions to ask. So how does the COVID affect our market, right? In my model, I'm trying to predicting the last half-hour return by the previous 12 half-hour returns. And I'm asking how does COVID affect the predictive power? Secondly, I want to see how which half-hour intervals are significant in predicting the R13 by statistical evidence. And my third question will be, is this model capable of predicting future data? To addressing the first question, I first use this model. So I'm trying to predict the 13th half-hour return by the first and the 12th half-hour return. The reason for choosing these 2 variables is because of a paper called Market Intraday Momentum. In this paper, the authors suggesting this model, and they give some detailed economical reasons why are the first and last half-hour returns of trading days so special, right? And I will not dig deeper into the economical reasons, but just analyze the model. And I will denote them as return 13, return 1, and return 12 to make it easier. So my hierarchical model will have these assumptions. I will assume that return 13 will be multivariate normal, standard at x time beta. X will be this matrix composing of columns 1, columns return 1, and the columns return 12. And beta will just be the coefficients for these 3 variables. And all the return 13 will be independently from each other with a variance of sigma squared. And my prior for beta will be a Zellner's Gaussian prior, because in this way, the scaling does not affect our posterior, right? Either I calculate the stock return in annualized form, in percentage form, or in this form, does not affect the posterior distribution. And in some literatures, researchers will use G times sigma square as the estimation of tau square. But as Professor said in class, it's not very natural idea to do so. So I just use the tau square. And my tau square will be inverse gamma of some non-informative hyperparameters. To compare, so to see the effect of COVID on the predictive power, I need first check what the model looks like in the normal period. So I do regression on the whole data set from 1998 to 2020 with about 5,000 times 13 data matrix. I first do a frequentist approach. I do fit a linear regression, and indeed we see that data R1, data of the return 1 and return 12 indeed have a significant predictive power on explaining the R13. And I also fit a Bayesian model, this hierarchical model, by RJAX. So my code is this. This is my model. I fit them on RJAX, and with an iteration of 50,000. So I obtained 50,000 samples from this MCMC sampling, and this will be the simulation to the true posterior distribution. As can we see that these two approaches are quite similar in results. The frequentist gives 5.77 as the coefficient for return 1, and the Bayesian gives 5.71 as the coefficient for return 1. And the credible intervals and the confidence intervals also agree with each other. So the red dots is the credible interval, blue dots is the confidence interval, and the first two are the intervals for return 1, and the second two are the intervals for return 12. So they're quite similar, but they are not the same because in the Bayesian inference, we are justified to state that we are 95% confident that the coefficient will fall between these 2 points. We're assuming the coefficients as something random, and it's much more intuitive than the frequentist inference. So though these two intervals agree with each other, we explain them in different perspectives. And there's another thing that is significant here, is that all the coefficients are well above 0, means that the R1 and R12 are very likely to be in the same direction as R13. And also, in the Bayesian framework, I am able to obtain this posterior distribution for the coefficients of R1 and R12. As we can see, it's quite independent, right? It looks like a bilateral normal with some correlation small. This means that assuming we already have this posterior distribution and we extract some samples from it. So for any sample, if the return 1 coefficient is large or not, does not affect the magnitude of the coefficient for return 12. So this is something we can't take for granted because the independence of coefficients of return 1 and return 12 are neither an assumption nor a result from some series. And then I'm comparing with the COVID-19 period. As can be seen, the credible intervals and the confidence intervals sort of disagree with each other in this data set. So the credible intervals contains more variance as the intervals are larger than the confidence interval. This is because in the COVID-19 period, the sample size is much smaller than the whole data set. There are only 88 data points in the COVID-19 period, in compare with about 5,000 data points in the previous section. So, and also in the COVID period, we can see that the coefficients for return 1 is still well above 0, just like in the normal time. However, the coefficient for return 12, or the predictive power for return 12, is now ranges from negative 0.7 to positive 0.3, which is quite large and also captures the 0. So we are uncertain how return 12 can predict return 13 in a COVID period. This is one of the the main difference that COVID-19 has affected the market. And another interesting observation is that in the posterior distribution of return 1 and return 12 in the COVID dataset, it just shows this significant negative correlation with a correlation of negative 0.43. This is interesting because actually this does not happen by chance. I have randomly selected 88 sample size from our whole data set, and out of 100 samples, there are only 2 of them that have shown correlation smaller than negative 0.43. So this negative correlation between the coefficients of R1 and R12 in the COVID dataset cannot happen by chance. This has to be due to some impact by the COVID into the market. And a conjecture I can think of is that during COVID, because the unprecedented pandemic and the high volatility, investors are extremely aware of the overnight risk. They don't want to leave their market. They don't want to leave their money into the market that long. So therefore, when the first half hour has a strong explanation power for R13, when it has a strong explanation power, so about this area, that means some news are released in the first half hour that affect the market very much, like an unemployment claims report or a COVID-19 death report that affects the market. If this is the case, then the investors will behave abnormally because of the risks conveyed by this information. And that leads to the R12 negatively correlated with R13. However, if the explanation power of R1 is relatively small, so about in this area, that means the day will just be a normal trading day and not really some informative information is released. In this case, the investor will just behave normally. So R12 will have a positive correlation with R13, just like in the normal time, right? The coefficients for R12 is well above 0. This means that if the R12 is positive, then investors are likely to enter the market and make some money, that driving the price in the R13 to be positive. And if it's negative in R12, then investors are likely to leave the market, which drives the price even lower in the 13th half hour period. And I also want to compare it with the subprime crisis, because as we all know, the subprime crisis in 2008 and the COVID-19 pandemic happening now are two of the most significant events in the stock history. And we can see some similarities here. In the subprime crisis, the R1 coefficients are still well above 0. The credit interval, the credible interval does not capture 0, just like the COVID and the whole data set. However, in the subprime crisis, the coefficients for R12 is still ranges from negative to positive, captures a 0, meaning that we're still uncertain about the effect of R12 on R13 during the subprime crisis. And I also observe another similarity, that is the posterior distribution of subprime crisis of the coefficients of R1 and R12 is also slightly negatively correlated, though that is not as significant as the COVID dataset. It's still negative. This observation means that investors' strategies are constantly evolving over time, right? Their response to a crisis will not be the same as their responses now. And also the research showing that before 2005, there aren't many frequent tradings occur, right? This is another evidence proving that the strategies are evolving over time. And in summary, in this section, I seek to construct the model by some economic reasons suggested by a paper called Market Intuitive Momentum. And in this approach, the observation is that R1 has a positive relation with R13 in both the crisis pandemics and in the whole dataset. And the relation is actually magnified in the crisis. As we can see, the mean in the whole dataset was 5.72%, while it jumps to 8.97% in COVID-19 and jumps to 15.23% in the subprime crisis. However, during the pandemic and crisis, the relation between R12 and R13 just becomes very volatile and uncertain. We can see the credible intervals for R12 in the normal time is well above 0, and have a very small credible interval. However, during COVID-19, the interval is so large that we cannot conclude anything from it, and also during the subprime crisis is also in a wide range that we're uncertain about the effect of R12 on R13. So this addressed my first question. This addressed my question of how does the COVID affect the predictive power? And in my second question, I will no longer use this economical regions for selecting models. I will just use statistical evidence to see which half-hour intervals are significant in predicting R13. So here it is. The evidence is computed by this formula. So I assume that each of the models are equally likely to be selected, then this will just turns out to be a triple integral of the likelihood respect to tau, sigma, and beta. And we can approximate by using pi f the beta hat and using a double integral to compute the likelihood, which turns out to be this formula. And I'm using the data from 2005 to 2016 as the training set, and 2017 to 2020 as the test set. So here's the result. In the top 50 evidence models, as we can see, the R1 and R12 indeed have a significant effect on predicting R13. But by the statistical evidence, we also see that R2, R3, R5, and R7 seems also to have a strong predictive powers in predicting R13. This answers my second question. And for my third question, can we predict future data from this model? So to address that, I'm going to perform a Bayesian model averaging technique. So I get the top 100 evidence models and I weighted them so that their probability of being selected sums up to 1. Why I'm only choosing top 100 evidence models, as there are about 5,000 models available, is because all the models after the top 100 just have so small evidence that we can just ignore them for simplicity. So to perform this, I also use RJAX, and I compute the posterior mean for beta for each of these 100 models, and store them as a matrix. Then with gauge sampling with 10,000 iterations, at each time step, I select a model by their evidence and obtain the corresponding beta estimated from the previous JAX model, right? So if the evidence is big, then it's more likely to be selected, and if the evidence is small, then it's less likely to be selected. So this is the given samples. As we can see, some of the entrants are 0, meaning that they are not selected by the models, but they could be positive in some entries along that column. And if I just averaging them up, this will gives me a pretty good estimation for beta. And in theory, that should perform better. That should perform better than just one sample. So here's the Bayesian model averaging parameters I get. The intercept is this, and there are the coefficients for each intercept. So as we can see, the first, 2, 3rd, and 12th, and 5th, and 7th all have a pretty big explanation power, while the rest of these 5 variables are not that significant. And these actually are quite similar as if we're just fitting a linear regression on the previous 12 columns. Say for x1, it gives 0.074, but here it gives 0.072. So it's quite similar, but there are some differences. And I'm assessing the performance on testing set by the sum of square error. It turns out that the sum of square error in the Bayesian average, which is 0.0114, is slightly bigger than that of the linear regression case. So the Bayesian average model actually performs a bit worse than the frequentist model in the test set. And also, it turns out that this model suffers some overfitting problem, which means that our initial model of only using x1, x12 having a smaller sum of square error than the Bayesian average model, even though it has such a small evidence. So this answers my 3 questions, right? So first, how does the COVID affect the predictive power? The COVID magnified the predictive power of R1 while making this predictive power of R12 uncertain. And during COVID, if the predictive power of R1 is strong, then R12 will be likely to be negatively correlated with R13. If the predictive power of R1 is weak, then R12 will be positively correlated with R13. And which half-hour intervals are significant in predicting the R13 by statistical evidence? Well, R1, R2, R5, R7, and R12 are significant. And is this model capable of predicting future data? No. The model will have an overfitting problem in predicting future points. However, this model still is capable of analyzing predictive powers doing in sample during some events. Thanks for listening.